Steve. Okay, we're going to talk about trigonometric substitution today. And basically, trig sub is used whenever you have a square root problem where you cannot use a u substitution. For instance, if you had something like this, dx, the integral of dx over x squared times the square root of 9 minus x squared. If I let u be 9 minus x squared, I get negative 2x, but I get it on top. So really there's no good u substitution that will allow me to solve this problem. So instead we make a trig substitution. So we make the problem become trigonometric to make the problem easier to work out, which I know will probably seem a little weird to you, but it actually is a very efficient way to work things, and we're actually going to prove a couple of things and why the formulas are what they are through doing this. All right, so you have three forms. You have a squared minus u squared. First of all, a is a constant, u is your x term. You have a squared plus u squared, and you have u squared minus a squared. And whichever form you have, it tells you which substitution to use for u. Now, you will not have to memorize these. This actually is not a topic that is tested specifically on the AP exam, but there are problems that you can do this way that make them easier. And freshman college calculus, you will probably be doing this in the very early part of the year, so like you might as well go ahead and learn it. We will be tested on it in our class, so I'm just putting it out there that it's not on the AP test, but you will be tested on it. Okay, so the first case is where you have a constant squared minus an x term squared, and the substitution you use is a sine theta. U equals a sine theta. So if I look at just this square root part, I have a squared minus and u squared. So that is u. So if I square that, that'd be u squared. So a squared sine squared theta. And if I simplify that, I can take out an a squared. I get 1 minus sine squared theta. And we know that 1 minus sine squared theta is cosine squared theta. So I have a squared cosine squared theta. Well, those can come out of the absolute value. You get an absolute value of a cosine theta. Okay? Now, what does that really tell you? Well, what it's really saying is that, okay, if I make a right triangle whose sine theta is u over a, which would give me a sine theta if I multiply. So if I draw a right triangle whose sine of theta, so opposite over hypotenuse, is u over a, then this third side is the square root of a squared minus u squared, which is this. Now, you might ask, well, where does this come into play? Well, if I look at the easiest combination in order to get the square root, remember, a is a number, but this has some x value to it. So if I look at this, this would be adjacent and hypotenuse. So I'd say the cosine of angle theta is the adjacent side over the hypotenuse. And if I multiply by a, I get a cosine theta equals the square root of a squared minus u squared. So that's the piece that comes together in how the case works. And it's you don't have to memorize that when you have a squared minus u squared, the square root's going to be a cosine theta, but when you set up the problem, it will kind of come to that, which I'm going to show you an example of this case now so that you don't have to wait to see that. So if we look at this example that I had earlier that I showed you, the integral of dx over x squared times the square root of 9 minus x squared. Well, I know that I have x squared, but I also have this a squared minus u squared term down at the bottom. So I know that a would be 3 and u would be x. So I'd have 9 minus x squared. Okay? So that over here transfers to x equals 3 sine theta, or sine theta is x over 3. So if I draw a right triangle so that the sine of theta is x over 3, opposite hypotenuse, then this third side is the hypotenuse squared minus the leg squared. Oh, look, it's that 9 minus x squared. Now you might say, well, yeah, but there's an x squared in the problem. There is, but I know how to get x squared. So now what I'm doing is I have a pictorial representation of what this problem is. And I'm going to rewrite that problem using trig functions. So I'm going to rewrite in terms of thetas. So the first thing I notice is I need a dx. Well, I have an x, so that means I can find dx. So dx, it's the derivative of 3 sine theta, would be 3 cosine theta d theta. I also notice that I need an x squared. Well, I have an x, so I can find x squared. X squared would be 3 squared sine squared theta, or 9 sine squared theta. And then I have this square root of 9 minus x squared. So I look to my triangle. The easiest representation of that would be saying cosine theta equals the square root of 9 minus x squared over 3, adjacent over hypotenuse. Again, I don't want the x in the problem. I want to make it as simple as possible. I just want this 9 minus x squared. So I make it the square root of 9 minus x squared over 3. So that means 3 cosine theta is then my square root of 9 minus x squared. So I come back to the problem, and I'm now going to rewrite it using this description. So dx is on top, so that's 3 cosine theta d theta, over x squared, which is 9 sine squared theta, times the square root of 9 minus x squared, which we said was 3 cosine theta. Now, looking what we have, we can do some algebra here, and we can cancel out the 3 cosine thetas. And so I really am just left with the integral of 1/9 times d theta over sine squared theta. Well, you may say, well, that doesn't look much better, Miss Merchant, but remember that sine squared on the bottom is better written as cosecant squared on top, so that's really just 1/9 times the integral of cosecant squared theta d theta, which actually does have an integral. We can integrate that. The integral of cosecant squared is negative cotangent, so this would be negative 1/9 cotangent theta plus c. So now going back to my original problem, I look at the picture and I do this. So my original problem was this dx over x squared square root of 9 minus x squared. So when I integrate that, I'll have negative 1/9 cotangent theta. So I look over here at my triangle. Cotangent would be, well, tangent's opposite over adjacent, so it would be adjacent over opposite. So it would be the square root of 9 minus x squared over x, and then don't forget the cupcake. So we were able to integrate this problem that we couldn't do any other way by introducing trig functions to allow us to get an answer. Pretty high level math, but pretty cool, I think. Okay, there are 2 other cases that can work like this as well. The next case that works like that is a squared plus u squared. So you have a constant squared plus an x term squared. So if I look at my square root of a squared plus u squared, if I use the substitution that u is a tangent theta, that would become a squared tan squared theta. If I factor out an a squared, I would have 1 plus tan squared theta. And 1 plus tan squared theta is secant squared theta. So the square root of all that would be a secant theta. And now coming over here and saying, okay, well, tangent theta then in my triangle is going to be u over a. So draw your triangle. Tangent theta is opposite over adjacent. So that means the hypotenuse is those two added together, squared and added together. So if I want just that particular representation. Remember, I want to put it with a, so let's see, from that it'd be hypotenuse over adjacent. So that's secant of theta equals square root of a squared plus u squared over a, or a secant theta equals the square root of a squared plus u squared. Ah, I see. Let's look at an example. I somehow missed a page. Hang on a second. Here's my example of case 2. Sorry that I had to shove it in there, but hopefully it will make sense. Okay. All right. So I have a squared plus u squared. Okay. So that means a is 1 and u is 2x, because 2x squared is 4x squared. So I draw a triangle so that, let's see, 2x would equal 1 tangent theta, or just tangent theta. So tangent theta is 2x, so that means tangent is opposite over adjacent. That means my hypotenuse is 1 plus 4x squared. So what do I need in this problem? I need a dx. Well, I know what 2x is. So what's x? X would be tangent theta over 2. So that means dx would be the derivative of tangent theta secant theta. So it'd be secant squared theta d theta. And then I need the square root of 1 plus 4 squared. And the easiest way to get that would be hypotenuse over adjacent. So that's secant theta equals square root of 1 plus 4x squared. So now if I go back and rewrite this problem using trig functions, I would have the integral of dx, which is secant squared theta d theta over 2. Then I have a square root on the bottom of 1 plus 4x squared, which is this. So that's secant theta on the bottom. And that's everything. So now I do some algebra. So that means I just have a 1/2. And the secant squared will cancel with the secant, and I just get secant theta d theta. And I know how to integrate secant theta because that's a green sheet rule. And so that is 1/2 the natural log of the absolute value of secant theta plus tangent theta plus c. So to my original problem then, that answer would be 1/2 the natural log, absolute value. Looking at my triangle, secant theta is square root of 1 plus 4x squared, plus tangent theta, which is opposite over adjacent 2x, plus c. So there is my answer to the problem. Okay, third case. I'm not going to prove it again because I can't, my notes are a mess. I don't know what happened, but it's on yours. I don't think I really need to prove it again, but let's do an example of case 3 where you have u squared minus a squared. So remember, u is your x term and a is your constant. So in this particular case, you would have u squared is x squared, so u is x, and a is 3 because 3 squared is 9. So we would say x equals 3 secant theta. So if I draw a right triangle, so secant theta is hypotenuse over adjacent, so secant theta would be x over 3. So we'd have hypotenuse over adjacent, which means this side is square root of x squared minus 9. So I need a dx, so I need to take the derivative of that. Well, the derivative of secant is secant theta cotangent theta, and the 3 goes along for the ride. I need an x squared, so that would be 9 secant squared theta. And I need the square root of x squared minus 9. So that easiest relationship would be opposite over adjacent. So we'd say tangent theta equals square root of x squared minus 9 over 3, or 3 tangent theta equals the square root of x squared minus 9. So, going back over here to the problem, this integral will become dx, which is 3 secant theta tangent theta d theta, over x squared, which is 9 secant squared theta, times the square root, which is 3 tangent theta. And simplifying, let's see, the 3's go, so I have a 1/9 left. Secant cancels with secant squared, so I have secant on the bottom and tangents completely go. So I have the integral of d theta over secant theta. Okay, again, that doesn't look any easier, but secant theta on the bottom is better written as cosine theta on top, and I do know whose derivative is cosine, it's sine. So that's 1/9 sine theta plus c, which means the answer to my problem is 1/9. Look at my triangle. Sine is opposite over hypotenuse, so it would be the square root of x squared minus 9 over 3, nope, over x, excuse me, opposite over hypotenuse, plus my cupcake. Okay? Now, 2 examples here to show you why the green sheet's rules are why they are. And the first one is dx is 25 plus x squared. We're integrating that, and we should know from our green sheet that the integral of that is an inverse tangent. It's actually inverse tangent of x over 5 plus c, and we also need a 1/5 because of this, because it's 1 over a. So why does that actually happen? Well, let's do this trig and see. So this integral could actually be written as dx over the square root of 25 plus x squared squared. And that puts it in the form where it is a squared plus u squared. So that means that u is a tangent theta. Well, a is 5, u is x, so x is 5 tangent theta. So x over 5 is tangent theta. So if I draw a right triangle, tangent is opposite over adjacent. That means my hypotenuse is x squared plus 25 or 25 plus x squared. Doesn't really matter which way you do it. So let's see, I need dx. So the derivative of 5 tangent theta would be 5 secant squared theta, d theta. I need this square root, so the easiest relationship is here. So from this angle, it's hypotenuse over adjacent. So that's secant theta. So that would be secant theta equals square root of x squared plus 25 over 5, or 5 secant theta equals the square root of x squared plus 25. So, rewriting the problem, I have the integral of dx is 5 secant squared theta, d theta, over the square root of 25 plus x squared, which is 5 secant theta, but I have to square that. So, that gives me 5 secant squared theta, d theta, over 25 secant squared theta, which means those cancel out. I just have 1/5 d theta. So when I integrate with respect to theta, I get theta plus c. Well, how do you find an angle? Well, those are inverse trig functions. So the easiest way to get theta is the x and the 5, which are, that's opposite and adjacent, so that's tangent. So you'll see that this is my 1/5 to get theta inverse tangent of x over 5 plus a cupcake. So that tells you why that inverse formula is what it is by doing that problem. Okay? I'm getting kind of long on this, but I think it is well worth doing this next example, and then I can save the other one for a warm-up in class. So hopefully it will be like maybe 25 minutes. So this next example is also inverse tangent, but we did this problem before, and we like, how do I handle that 9? Do I have to multiply by a 1/3 out front? Well, it turns out that you actually do. And so let's look at this problem. Remember, this can be again written as dx over the square root of 4 plus 9x squared squared. So that means a is 2, u is 3x. So a squared plus u squared is u tangent theta. So that means that we're using u equals a tangent theta. So 3x equals 2 tangent theta, or tangent theta is 3x over 2. So if I draw my right triangle, there's my theta, so tangent's opposite over adjacent, which means this is 4 plus 9x squared. I need a dx, so let's see, what is x? X would be 2 tangent theta over 3. So dx would be 2/3 secant squared theta d theta. And then I also need the square root, so the easiest relationship is here, and it's hypotenuse over adjacent. So that would be secant theta is square root of 4 plus 9x squared over 2, or 2 secant theta is the square root of 9 plus square root of 4 plus 9x squared. So going back here to my original problem, we have the integral dx. So I have 2 secant squared theta d theta over 3. And on the bottom I have the square root, which is 2 secant theta, but that has to be squared. So we actually have 4 times 3 is 12 with a 2 on top, so that means I have 1/6. And again, I'm just left with d theta, so this is 1/6 theta plus c. And the easiest theta is opposite over adjacent, which is tangent. So it's 1/6 inverse tangent of 3x over 2 plus c. So we see why we have out front what we do when we use that formula. All right, I'm going to do the last couple in class. I'll do example C and D in class so that I don't take any longer of your time.